Hydrogenation of alkynes. So alkynes are hydrocarbons that contain a carbon-carbon triple bond, such as the 3-hexene that is drawn here. Alkynes undergo most of the same reactions that alkenes do. It is important to remember, though, that alkynes are less reactive than alkenes. So if we are to look at the hydrogenation of an alkyne, the hydrogenation will use the same conditions as for an alkene. So we will add hydrogen gas in the presence of an active metal catalyst such as palladium on carbon. In all hydrogenation reactions, the hydrogen gas gets absorbed onto the surface of the palladium, and then the alkyne or the alkene reacts at the surface. Both of those hydrogen atoms are added at the same time to the same face of the alkyne or alkene, and we call this a syn addition. So after the first equivalent of hydrogen is added to the alkyne, the product will be the product where both hydrogens have added to the same face, so both R groups are also pointing in the same direction. And so this initial product is a cis alkene. Now this alkene is more reactive than the alkyne starting material. So that means that this reaction will continue. Also, whenever we do a hydrogenation, we have a large excess of the hydrogen gas. And that is because of how the reaction is set up. The hydrogen gas comes from replacing all of the air in the reaction flask with hydrogen gas. And so there is always a large excess around. If we have a more reactive alkene, the reaction will keep on going. So we will see another equivalent of hydrogen gas adding. So we can have a second equivalent, and we still have the catalyst around. And so when this second equivalent adds, the product will be an alkane. So overall, we will have added the first equivalent of hydrogen and then the second equivalent of hydrogen, so that the product is the alkane. If we wanted to do this reaction and have the reaction stop at the more reactive cis alkene, we can do that. We need to change the catalyst. So if we wanted to stop the reaction and get the cis alkene, we would still use hydrogen gas, and we would still be using palladium as a catalyst. We would just be using a poisoned palladium metal catalyst known as Lindlar's catalyst. So Lindlar's catalyst is, as we said, a poisoned metal catalyst. So this is a palladium catalyst that has been poisoned with quinoline and either barium sulfate or lead acetate. And that stops the reaction at the cis alkene. So let's do a couple of more examples. So if I start from this alkyne, which is 1, 2, 3, 4, 5, 6. So this is 2-hexene. If I treat the 2-hexene with our normal hydrogenation conditions, so hydrogen gas, which is always present in excess, and palladium on carbon, we would expect that this reaction would go from the alkyne all the way to the alkane. If I started with the same 2-hexene, and in this case, still use the hydrogen gas, but change the metal catalyst to be the poisoned Lindlar's catalyst, then we would be able to stop this reaction at the cis alkene. And so the product would be 1, 2, 3, 4, 5, 6, the cis 2-hexene. So the product from just one equivalent of hydrogen gas, and the reaction's still occurring on the surface of the metal, so both of those hydrogens are transferred at the same time to the same side.